Main is a single return statement. That's pretty awesome. All right, I will have to check that out. So, it's recursive, several hundred characters long. Interesting. Oh, sweet. Yeah, that's righteous, man. Cool. I'll have to play it. All right. Any questions? How's PA2? Good use of your sleep time. Oh boy. PA2 was going great until I implemented the test files that we were given. Oh, what happened then? Or rather, did you try it with your own test files first? Because if it works on your test files, that's a good sign. It doesn't seem to add words to the hash anymore. Going to figure it out later today. It works on my own. Okay. So yeah, might just be something subtly different about how it's being called. All right, so before I forget, tomorrow I'm going to do Open Lab again, so I won't lecture on anything in particular, but I'll be here. And if you want to work on PA2 or PA3, if I get that posted or anything else, you can come in and ask questions, answer questions, etc. So we'll do that as an Open Lab tomorrow during class time. All right. Well, if there's no questions, let's continue where we were yesterday. Let's look at try catch and finally blocks. Does Java have a concept of falsy? What is falsy? Like falsish? No. So if I understand you correctly, so in C we can use 0 as false, non-zero as true. That doesn't work in Java, right? If you're expecting a Boolean, you have to use a Boolean or something that evaluates to a Boolean. And so you can't have an expression that evaluates to 0 and use that inside an if statement, for example, which I kind of miss. All right, so let's dig further into cool. You're welcome. Into try catch blocks, and we were talking about this yesterday, and I mentioned that you can have multiple catch statements. So we'll just make a main. And a main method. And let's generate some exceptions, right? That's always good to do. So let's make an array. So we'll make an array of 10 integers. And let's ask the user to type in a number. We'll ask them for an index. And I'm going to use a scanner on system.in to read in a line from the user. And I'm only going to read one line, so I'm going to do something really kind of quick and dirty. I'm going to say, you know, string temp equals new scanner system.in dot next line. All right. Now, if I was going to do more than one line of input, I would construct the scanner and save it in an object, and then I would say object.nextLine. But since I'm only going to read in, you know, one line for my whole program, I'm just constructing a scanner here. The result of this part of my statement is a scanner. Scanners have a nextLine method. I'm going to call that nextLine method. All right. I'm going to do something a little more extreme. I'm going to convert that input to an integer. So the integer class has a static method called called parseInt. There we go. Called parseInt. ParseInt takes a string and returns an integer. Okay, it's a static, so I get to this method by saying uppercase I integer.parseInt, parentheses, and then I pass a string. So statics always feel different from the way we call methods that are part of an object, like, you know, string.length paren. Here we're just going to access this by putting in the name of the class integer.parseInt, and then we're going to pass the argument in that we want to parse. And by the way, there's a parseInt that lets us specify a radix. So if we want to parse a hexadecimal number, we could do parseInt string comma 16, for example. So we're going to do a straight parseInt. And what do I want to parse? Well, I want to parse the string that came back from next line. So I'm actually going to get rid of this temporary variable. And I'm just going to say integer I equals integer.parseInt parentheses, all of this stuff. Okay, that's a needlessly complex looking line, but it's intentional. I want you to really kind of like immerse yourself in this idea of objects, and objects have things, right? This is an object that corresponds to standard in. This is a scanner object that will read from standard in. This whole thing is an object. It's an object of type string. And it will be the string that comes from, you know, typing and hitting the enter key at this point of the program. And then this is a static or a class method that ingests a string and returns an integer, and I'm saving that integer in I. All right, so let's do the following. Let's say my data bracket I equals 1000 divided by I for no particular reason. I'm just going to pretend that I'm like a graffiti artist and this is like my tag, so I write U's with a 9 in the middle of them. So so this will not do a whole lot. I'm going to have to import the scanner class. But you know, I can what did I call it? Oh, my bad. Alright, so I can put in a number and it, you know, sets an element in my array equal to 1000 divided by 3. Not a whole lot happening right now. So what happens if I put in an illegal value? So suppose I put in a value like 999, right? I'm going to try to set element 999 of the my data array. I'm going to get an exception. And the exception is array index out of bounds exception. Alright, so what we can do is instead of having this, you know, print out this random message on the screen and then exit abruptly, we can try to catch that. So I'm going to put a try statement around here. and I'm going to try to catch that exception. And I can, just put in whatever name I want for a placeholder here, which will be given an exception of type array index out of bounds exception that I can then interrogate to find out what happened. But we'll just print a message here. And I'll just say I is not a legal index. And I'll return. And there we go. Alright, so now we're going to try to make this assignment. And if it succeeds, we'll skip the catch block. We'll come down here and say thank you. If we put in an illegal index, we'll generate this exception. This catch block will trap this. And we'll go into here and we'll print out this misspelled print message that says I is not a legal index. All right, everybody got the idea what's going on here? So we compile it and run it. Legal index works exactly the same as before. Put in an illegal index, and we get a nice message here, -1 is not a legal index. Now we chose to exit by returning, but we could have done something else. We could have said try again and gone back and gotten another input, or done something appropriate, deleted files at random, whatever. All right, so that's the basic try catch that we finished with yesterday. And exception is a class, and there's a number of other exceptions that are derived from this. So the one that we're working with right now is array index out of bounds. Which I don't see in here. Alright, that's okay. Alright, so I'm also setting the element equal to 1,000 divided by I. So something else can go wrong in here, right? If I run this, I could put in a 0, and my data bracket 0 is not an illegal index, but I'm going to generate a divide by 0 error. Right, so the exception here is arithmetic exception. So we can put a separate catch block in here just to catch that exception. So we'll do a catch for an arithmetic exception, and here we'll print a message saying division by 0 question mark. Alright, so legal index, no issue at all. Illegal index, we get a message saying that it's not a legal index. Division by 0, we get a message saying we're trying to divide by 0. Right? But in no case is the program simply abruptly exiting, right? Printing out some kind of abnormal message and then just exiting. It's doing what we want, right? We can set up anything that we want in here. We're returning, but we could do, something else, and let the program keep continuing to run. So this is a very tight try block, right? There's one statement inside here, and if any of these exceptions happen, then we'll go into the corresponding catch block. If an exception happens that we don't catch, then the system will print out the usual error message, and the program will exit. So another possible exception would be typing in something that's not a legal integer. And if I do that, then up here at line 11, when I'm calling integer.parseInt, right here, I'm going to get a number format exception. Okay, so that's at line 11, which is up here. Now, the really proper thing to do might be to put another try-catch block around this statement. But just to illustrate, how big these blocks can get, I'm just going to move this try statement up here. So that it looks like that. And I'm going to put another catch block down here. And I'm just going to say, catch anything of a type exception. And I'm just going to say some other error occurred. And I'm going to print out the two-string version of that exception so I can see what happened. And I'll return. And there's our try-catch block. All right, yeah, we got a question about Java docs, so we'll come back to that in a little bit. Exception. Thank you. Maybe we'll fix sun me. All right, so this seems reasonable, but this is going to give me some strange compile errors. Give me this error that I cannot be found, right? This is the same thing that happened when we first moved scanner into a try-catch block. The variable I, right, is declared right here, but it's declared inside the try block. If this parseInt fails, right, and we come into this block, for example, I does not have a existence, right? I is scoped between here and here. So same thing we did with the scanner. We can declare I outside and then give it a value inside our try block. And that might look more reasonable, but it's still going to complain. And now the complaint is variable I might not have been initialized. All right, so this is kind of weird, okay? This is a case of the Java compiler is not as smart as you are, and you have to kind of help it along. So let's look at the logic. I'm declaring I to be an integer. I haven't given it a value. Here I'm going to do parseInt and try to convert a line of input into I. That might cause an exception. If it does, I'm going to come down here, I'm going to print out some other error occurred, and I'm going to return. Okay, if this line succeeds, then this might cause an exception and I might end up down here, but at that point I know this line has succeeded, I has a value. So the error message from the compiler is variable I might not have been initialized. Well, in fact, it's guaranteed if you get to this point that it's been initialized, but the compiler can't tell that, right? It would need to understand not just the syntax but the semantics of the program, and it doesn't do that. It looks at it and it says, if this statement fails and you end up down here, I won't have a value. So it's going to refuse to compile, even though there's not a real problem with this code. All right, so what do we do about this? Well, this is a case where you might want to just throw a band-aid on, or you might want to put a try block just around this statement and the corresponding catch block for that. So I'm just going to band-aid it. I'm going to give I an initial value up here. And that's a bit of a hack. But it's really there just to get the compiler to relax and say, okay, I'm fine with running this. And so now if we run it, legal index, no issue. Illegal index tells us not an index. Division by 0, it tells us dividing by 0. And if the parseInt fails, it will come down to that last catch block, and it'll say some other error occurred, and I had it print out the value of that argument, which says, it's a number format exception, and here's the string that I was trying to parse. So we're getting pretty fine-grained now in the processing of these exceptions. And the way the exception handling works is, if an exception occurs, it will look at the first catch block, and it will say whatever the exception is that occurred is it one of these? Is it an array index out of bounds exception? Which means either it's an array index out of bounds exception, or it's something that was derived from this. It's an extension of it. If it's not one of those, it'll say is it an arithmetic exception or something derived from that. If not that, then it will say is it an exception or something that's an extension of exception. And every exception is an extension of this class. So this is basically a catch-all. Right? Any exception of any type will always be caught by a catch block if you make the argument a type exception. And each of these exceptions is a class by itself. Right? Array index out of bounds is an exception. It is a class. Right? And it comes with methods, but not particularly profound methods, right? Basically the methods that you get from things that this is extending, like throwables. So we can get a message, we can get a stack trace, we can print a stack trace, and so on. And we can construct these ourselves if we want. We can make one of these things, right? By passing a constructor, we can make one of these things and give it a particular index, right, if we want to throw errors, throw exceptions ourselves. All right, so good on this so far? So we're going to add one more level of complexity here, which is the finally keyword. So after all of these catches, we can put in something which says finally. And we'll just print a message saying we're inside the finally block. All right, so let's look at the whole structure. We're going to try a statement. Let me get rid of this space here. We're going to try a pair of statements. If it succeeds, we will come down to the finally block and execute this. If an exception occurs, it will start looking at catch blocks, and the first one that matches the exception will get executed. And whether it succeeds or fails, whether it gets all the way through the try block or it jumps down to a catch block, you're guaranteed it will always execute the contents of the finally block. And this may look kind of strange. So if I put in, a division by 0, it tells me division by 0, and then it says inside the finally block. Okay, so what's weird about this? Just looking at my code, what's it supposed to do after it says division by 0? It's supposed to return. I said print division by 0, and then I said return. And guess what? It printed out division by 0, but it apparently didn't return right away. It came down to this finally block that said, print this, and then it did a return. So it's a little bit of a weird flow thing, right? In a catch block, even if your catch block says return, it will still come down and do the finally block. Okay, I don't know if that's a bug or a feature. Depends on your perspective. Seems a little strange to me, but that's how it works. So you can do some kind of wrap up in here, right? And it's always going to fire even if you say return. Now, if you don't say return, yeah, it is totally. If you don't say return, it won't continue through catch blocks, right? It'll only fire one catch block, but then it would go into the finally block. So we can take these out. And now if we put in a bad index, right, it says not a legal index, it does the finally block, and then it came out of the whole try catch structure, and it did my thank you at the very end. All right, so finallys can be a little counterintuitive that way. I think only one catch will fire at a time in response to an exception. I think only one catch will fire total in response to an exception. And it's the first one going from the top that satisfies the criteria. And again, you know, if you get really kind of like sloppy, like if your program is generating an exception and you're told you can't have any exceptions, you might put your entire, you know, 500 line method inside a giant try statement, right? That's really not what you're supposed to do. You're supposed to not have exceptions, and if there's a possibility of an exception that you can't help, right, you put a little piece of, you know, try statement around that, and you put a catch block to handle the exception. Otherwise, you're really just kind of band-aiding some kind of what's probably a problem in the design. All right, so an earlier question about documentation. So let's click on a link from chat. So, and I think this is similar to the documentation that I keep pulling up. And there should be a size in there. So there's 6 occurrences. Yeah, so there's the size method. And then you can click through to it. So this documentation takes some getting used to. And, you know, if you start off here, you've got, like, you know, all the packages, utilities and I/O and so on and so forth. And you can click through from there to the individual classes. So you can find a hash map in here, or hash set, hash map, and so on. But there's search options, and how did you miss that? Because the whole page looks the same, right? I mean, it just kind of goes on and on. So it's easy to miss stuff. Searching will sometimes help, but not always. Depends what you're searching for. And, you know, sometimes Googling is faster. But the more that you kind of get used to the look and feel and layout of these pages, the more useful they're going to be. And having like a single source for, you know, your go-to for questions about classes is going to help, as opposed to, you know, just Googling and here's a Stack Overflow page and here's a Geeks for Geeks page and so on and so forth. And when we talk about the Java doc command, right, we'll see how to produce documentation like this for our own classes, which is fun. And we'll probably do that in a future programming assignment. But you can basically just put comments in throughout your code and then run a Java doc command, and it produces HTML pages that look just like this and are all hyperlinked and so on and so forth. All right, so any other questions on this? There is a Java debugger, JDB. I haven't had much luck with it personally, but I don't think I understand the philosophy of it. When we get to Eclipse for programming assignments 4 and 5, there's a debugger in Eclipse that works pretty well. But you can mess around with JDB if you like, and if you figure out how to use it, let me know. Because like I say, I just don't think it's working the way that I philosophically want it to, and so I've resisted it. Eclipse is an IDE. It's an integrated development environment that we'll be using for making GUIs and doing some of those higher level things. And I'm going to post a video that starts with a completely bare bones VirtualBox Linux environment, just Ubuntu 18, and goes through installing Eclipse, Java, Window Builder, Swing, the pieces we're going to need for PA4. And I'll post that up sometime in the next few days. And it's not a bad environment. It's you know, gets quirky sometimes, but it's free and it's moderately well supported, and you can do VI inside it. And it mostly you can get it to stay out of your way. Like most IDEs, it tries to kind of control how you write code, so it will complete your statements for you. It will turn your whole file red because you haven't typed, you know, a closing parentheses yet. It will offer suggestions for, you know, what you might be typing. It's kind of like Clippy on steroids. But you can turn off most of that stuff pretty easily. It's not like some IDEs that are almost impossible to disable, and they really kind of force you to, you know, place your finger on the W key and apply pressure now, you know. Yeah, so we'll dig into Eclipse in another week or two. Once PA3 is underway, we'll start using Eclipse, and we'll start playing around with making graphical interfaces, and that's the main reason. Yeah, and there is a VI plugin for it that works really well as long as you turn off some keyboard shortcuts. So we'll have fun with that. It's actually a decent way to write stuff in Java. All right, so let's talk about trees. So we're going to shift gears here. PA3, you're going to be building trees and using them. They're going to be binary trees, but they're not going to be search trees. Okay, they're going to be what are called decision trees, and we're going to write a program that can ask you yes/no questions and figure out what you're thinking. So a mind reader program. And we're going to build our trees very similarly to how we did in 222. We're going to use a lot of recursion, but we're going to do this in Java. And we're not going to use a built-in tree library. We're going to build it ourselves. So I want to go through some of the basic framework for that, and kind of see multiple catches are possible. Oh, cool. Okay. Oh, yeah. Okay, you can OR them together. Cool, good stuff. Okay, so yeah, we just got some code in chat on how to do multiple exceptions in a single catch statement. So that's cool. All right, so we're going to have a tree. These decision trees are actually going to be completely full. Every node is going to have 2 children, except for the leaf nodes who have none. And we're going to call this thing a tree, so that's going to be a class we define. And let me show you, let's see, we've got 14 minutes. We're not going to be able to develop this all the way, but let me show you how we want to use this tree class. So I'll make a T main. I'm going to make a tree called T. And for this, I'm going to do a binary search tree of integers, right? Because that's what we're used to from 222. So I'm just going to say t.add. I'm going to add some values. And then when I want to traverse my tree, I'm just going to say t.print. And that's going to do a left node right traversal. All right, so that's the class we're developing right now. It's just a basic binary search tree. You can add things by using an add method. You can traverse by using a print method. All right, pretty straightforward. So what is our tree class going to look like? Well, we're going to need a root, right? We always got to have a root of a tree. So we're going to need to define what a node is, and whatever a node is, that's what the root's going to be. And this can be initialized to null. So null root means there's no nodes in the tree. And so we need to make an add method and a print method. And that's pretty much going to be our whole tree class. Minimal functionality. What's going to be interesting here is when we try to do the recursion, right? So suppose we're saying tree T, and we construct it, and we've added some stuff, and let's just think about t.print. Okay, what's the recursive way that we print a tree? We recursively print the left subtree, we print out the data value from the root node, and then we recursively print the right subtree. When we try to do that in Java, it's a little awkward, right? Because when we say t.print, we're going to find ourselves in this method here, and we have this root, right? And we can say, you know, if root.left is not null, then let's print root.left recursively, right? But root.left is going to be a node, not a tree. Okay, this is a fundamental kind of schism. So this is our tree class. So T right here is going to be a tree, but t.root is not a tree, it's a node. Right? And this is different from 222. 222, a root was a node, the root's left subtree was a node, the root's right subtree was a node. The handle that we used to get a hold of our tree was a node. But in this case, our handle is going to be a tree. So we're going to do something a little different here. We're going to make this basically just a wrapper that says call the roots print method. And we're going to make this thing a wrapper which says call the roots add method. And we're going to define the actual print and add methods inside the node class. Okay, but we're going to have to be careful up here. Because with an empty tree, what's the root? The root's going to be null. And if root is null and we call the add method, we'll get a null pointer exception. So we're going to have to deal with the edge cases explicitly up here in the tree class. So we're going to say if root equals null, root equals new node, we'll construct a node with a value of n, and we're done. Otherwise, root is not null, so we'll call root's add method. And for our print method, if the root is null, we'll just return, because there's nothing to print in an empty tree. Otherwise, the root's not null, so we can call the root's print method. How are we doing time-wise? Oh, we got 8.5 minutes. We can make this happen. All right, we're almost done. We got the main method, we got the tree class. All we got to do is make the node class, right? And the node class is going to have an add method and a print method that do the usual things. All right, so we'll make a node.java. So it's going to have an integer piece, which we'll call data. It's going to have a left, and it's going to have a right child. And I'm going to make a constructor for this, which takes an integer and creates just a node containing that in its data value. So data equals n, left equals right equals null. That's our constructor. All right, let's do the add method. So how do we add to a tree? We compare the value we're adding to the root. If it's bigger, we add to the right. If it's smaller, we add to the left. All right, data is the value of this root node's data value. So if n is bigger than data, we want to add to the right. So we're going to say right.add n. Otherwise, ignoring the possibility that it's equal to the root, we're just going to add to the left. So we're going to say left.add n, and we're going to return. All right, does that logic make sense? So this is 224 trees. If the number is bigger than the root node, add it to the right subtree. The right subtree is right? That's a node which is the root of the right subtree, so we call that node's add method. But we still need to deal with a base case, because it's possible that there is no right subtree. It's possible that right is equal to null. In fact, we're guaranteed eventually right will be equal to null, because when we keep moving down the tree and we get to a spot where we want to move to the right, but there's no node there, that's where we go ahead and we insert our new node. That's the base case of the recursion. That kicks us back up the rabbit holes. So we need to put a check in here. If right is equal to null, we'll go ahead and construct a new node with a value of n, and we'll set right equal to that. Otherwise, we'll call right's add method. And it looks different from C because of the objects, right? Because we actually have this class called a tree that we're going to construct, a T from, and use that as our handle to our tree. But to do the recursion, since the tree is made up of nodes, not trees, right? To do the recursion, we need to actually have those recursive methods defined as part of the node class. So it's kind of the OOP that forces us into that. All right, and then same thing here on the left. If left is null, then that's where we want to add a new node. So we go ahead and we make a new node and we set left equal to that. Otherwise, we call left's add method, and we return. And that should be our whole node class. Guess I'm still in the exceptions directory. Okay, that's fine. All right, so let's see if this compiles. All right. So compile errors, go to your first error, right? In my main program, it says T might not have been initialized. And in fact, it has not been initialized. So that's a very reasonable error. Alright, go to your first error. Public void add. Yep, okay, so lots of typos here. So that's in tree. Alright, don't put your semicolons at the end of that. One error left. Cannot find symbol root.print. So 17. but we didn't write a print method. Alright, we've got 2 minutes left. We can do a left node right traversal in 2 minutes. So how do we print the tree whose root is root in this case, right? We're inside a node, right? So the node exists, right? But we don't know if the left tree exists or if the left tree is null. So we can do the following: if left is not equal to null, print out the left subtree, and then print out the data. And then if right is not null, print out the right subtree. And that should be our print method. So let's go ahead and run tmain. So we're adding in these values to our tree, right? And we're adding them out of order. And then when we print, they should come out in order because it's a binary search tree. There you go. Sorted from smallest to largest. So the only thing that's really different from doing this in C is that we kind of have this outer layer around it, right? The node class, the methods in there look and feel like the recursive methods that we had when we did this in C. But we're adding an extra layer outside, which is this tree class, so that we can construct a tree without necessarily having a root. If we tried to just use the node class, right, we would have to do something like, node tree equals null, and then we'd have to, set that equal to the result of adding, and it makes things quirky. So we put this outer wrapper around it. All right, so this code's up on the server if you want to eyeball it, think about it, and ask questions. So open lab tomorrow. Keep working on PA2. Let me know if you run into questions on that tomorrow or in office hours. And I will see you next time.